for lack of a better word, all right? So that in complex comparisons, what we're really doing is comparing, let's say, the mean of these groups to the mean of those groups, okay? So that we're still comparing two things, but they have more components to them. That's a complex comparison. So we have to talk about how we calculate this complex comparison. Okay, let's take a look at this. Imagine I have 5 groups of antidepressant. Okay, I have 5 groups of antidepressants. And here are the groups. We'll look on top. A, B, C, D, and E. Okay, I have 5 antidepressants, A, B, C, D, and E. A and B come from the family of antidepressants called MAOIs. All right? C, D, and E come from the family of antidepressants called SSRIs. Now, I may want to compare all of these drugs to each other. Those would be pairwise comparisons, A and B, A and C, A and D, right? I could make all of those comparisons. Those would be pairwise. But maybe I'd like to do a more complex comparison. That is, comparing the mean of the MAOIs to the mean of the SSRIs. Okay? In which case, that would be the mean of groups A and B compared to the groups of C, D, and E. All right? That's a complex comparison. So how do I go about doing that? Well, we have to do it in this fashion. All right? Just look at this for a minute. This is what I said I want to do, right? Which is to compare the mean of A and B to the mean of C, D, and E. Right? Does everybody see how that's coming about? Notice something. All I'm doing, setting this up here, is changing it into something like when we had 2 groups, you know, x bar 1 minus x bar 2. There are just more components to it now, but it's this thing minus this thing. Okay? To figure this out, the magnitude of this difference using these population parameters is this Greek letter psi. It's the Greek letter psi. And again, what that is the magnitude of the difference between the mean of A and B versus the mean of C, D, and E. Okay? All I'm doing is calculating how much that difference is. Now, it's not always so useful to work with it in this formula. So we're going to change it. We're going to expand that so that each value, each mean, right, the mean of each 5 groups, has what we call a coefficient in front of it. A coefficient. That is, we're going to take each of those means and multiply it by a number. It tells us how much to weight the particular mean. Now, if I want to change this, if I want to expand it, all I do, you notice, right? It's 1/2, but it's 1/2 times the mean of A plus 1/2 times the mean of B. Notice this. This is negative, right? Because it's minus 1/3 times the mean of C. But that negative sign expands to all those terms, so don't forget that. All right? So all I've done is expanded that out so that now each mean has a coefficient in front of it that tells us how much to weight the mean in its part of the equation. Okay? Good. Now, I could take this further because what I'd really like to do is change this into whole numbers. Why? They're going to be easier to work with. And when you do this in SPSS, it will ask you for these coefficients. Okay? When you do a contrast in SPSS, I mean, it's much easier than doing it by hand. But one of the things it's going to ask you is, what are the coefficients? It wants to know the order of the groups that you're talking about and the coefficients for each one. So let's get the coefficients here. If I want to change these to whole numbers, what do? You know this. If I want to change this to whole numbers. Oh, good morning, people. Yeah.
Just use the denominators?
Use the denominator. What denominator, though, am I going to multiply everything by? The common denominator, right? What's that going to be here? 6. Yeah, I multiply everything by 6. So what's going to be the coefficient in front of the mean of A? Good. same thing here. Here is going to be, it's actually going to be minus 2. Don't drop that negative sign. So that the coefficients I actually have here are 3, 3, minus 2, and minus 2. It's good to keep that in mind. Like I said, SPSS is going to say, okay, you want to do a contrast? Great. What are the coefficients? This is what it's going to mean, because it wants to know how much am I weighting each of these groups, or each of these groups means in this formulation. Okay? So now, let's talk about what this is, okay? This is a linear combination, but even more so, look at the coefficients for a moment. If the coefficients add up to 0, this is what we call a linear contrast. A linear contrast. Okay, that's what SPSS will think it's doing, a contrast. Specifically here, a linear contrast. It's linear because we're just adding and subtracting, right? There's no exponents there. So it's a linear contrast if these coefficients add up to 0. Now, this is the more general formula, right? I could write this out for everything, but this is the more general formula. My psi is equal to each coefficient times the group mean that you're talking about. Add it up. Okay? Yeah. Each coefficient, right, C sub I, the coefficient for each group, times the mean of whatever group you're talking about. Right? So in this case, it would be 3 times the mean of A. But you have to do that for each group and add it up. Okay? Everybody still with me? Questions? Okay. All right? So this is a linear contrast. All right? What you're doing is you're calculating a value that you're going to test. You're going to do a hypothesis test on this value. Because again, remember, in the simplest of all situations, it's just one mean minus another mean. That's all we're really doing here. I could even do that. If I just wanted to compare A and B using this kind of idea, I could do that. But what would the coefficients be? It would be 1 and minus 1, and then these 3 would be 0. They'd fall out. They'd fall out. Okay? That would be just comparing group 1 to group 2, or group A to group B. Okay? So just try to keep that in mind, that that's all you're doing. It's like finding the numerator of a t-test. This thing minus this thing. Okay? But now what I have to do is I have to take this and turn it into something that I can test. Now, in theory, you could do some kind of t-test with this. We're not going to do that. He recommends in the book using an ANOVA formulation, an F formulation. Now, we know what the F test is made up of, because we've only done simple F tests now with one factor. What was my F with one factor, one independent group's factor? What was F? Real simple fraction. I told you should keep in your brains. Yeah, MS between over MS within. So what I have to do is I have to get from this to a way to test this using that kind of formula. Okay? So these linear contrasts, what we're going to be doing. Now, the mu, the psi, that was for population, right? Those were parameters. Let's talk about it with our sample statistics, because this is really what we're going to be doing. Instead of psi, if you're using sample statistics, which is all you're going to be using, really, it's the letter L. It's the letter L. He says L for linear contrast. Is equal to each coefficient times the sample mean. That's just what we did before. But this is just with the sample statistics. Okay? I said this before, but let's see if there's anything worth reminding ourselves. Right? Linear contrast is just a different score involving group means. That's all it is. Can be simple pairwise. That's what I showed you with the 1 and the minus 1. Or it can be complex like we've just looked at now. All right? To test for significance, what we're going to do is we're going to take L and turn it into an SS contrast. An SS contrast. Because, right, if my ANOVA is MS between divided by MS within, so I have to get to an MS between type thing. How do I get to an MS between type thing? Well, I start out with an SS between type thing. And then how do I get to a mean square from a sum of squares? Divide by degrees of freedom. So that's what we're going to be doing. Okay? So this is going to be called SS contrast. It's like SS between. But you're testing a particular pattern here. So SS contrast is going to be N. Now notice something. This formula is for equal ends. On the next page is going to be the formula for unequal ends. If it's equal ends, so that N is going to be the number in each group times my L squared divided by the sum of all of my coefficients squared. We're going to do examples, so don't stress too much about it. What if your n's are not equal? Well, then you have to make an adjustment and divide each coefficient by its own n. Okay? It's just a slight difference in the formula. Okay? Now, what were the degrees of freedom for between? Try to remember, right? MS between we got by SS between divided by degrees of freedom. What were the degrees of freedom for between? Yeah. It was k minus 1, where k was the number of groups that we were doing. Okay? In this contrast situation, what do I have? I have this thing minus this thing. So it's essentially like two groups. So if that's the case, how many degrees of freedom would I have? I would just have one. I'd have 1 degree of freedom. If I have only 1 degree of freedom, that means that my SS contrast is equal to my MS contrast, right? Because SS contrast divided by the 1 degree of freedom equals my MS contrast. It's the same thing. That's what this is saying. MS contrast equals SS contrast. Okay? So now we have MS contrast. All we need is to know what the error term is, right? The denominator of my F ratio. And the error term is MS within. MS within from your original ANOVA. Okay? Now, this formula is only for equal ends. If it was for the unequal ends, you'd have to replace that. The more generic form would be this. Okay? That's really what you're getting to. So whether you have equal ends or unequal ends, he just happens to have that formula in the book, but you would want it more generic so that you could do it for unequal ends. Okay? So now, yeah?
You said it's the error term. Is that also sometimes used as MS error? I know in the SPSS assignment it's passed.
It's what?
MS error.
Well, what is MS error? MS error is the denominator of your F.
Right.
So in this case, it happens to be MS within.
Okay.
It's not always the case. When we get to repeated measures ANOVA, it's not going to be the case. But all you know right now is that MS within is our error term. Okay? That's why I brought up the use of the word error term. It's helpful in a more generic sense. Okay. So what we're going to do is we're going to find an ANOVA with that, and then we have to talk about how we test it afterwards, which critical value to use. The critical value you use will depend on whether you decided on doing this contrast before you looked at your data or after you looked at your data. The probabilities change depending on whether you've looked at the data or not. So it's going to be different. All right? So let's first do an example with the computations, and then we'll talk about how to test it. This I would like. This is not working so well for me. Hang on a sec. Let's see if that's any better. Okay, so what we're going to do is we're going to go back to this question. Remember this question, the bicycle riders and different diets? We did this as an ANOVA. And we also did this with the HSD. Now we're going to test a contrast. Okay, so I'm going to write the means up again, up top, so we can see what we're doing. All right, those were our means. We did this ANOVA. We found out it was significant. But now I would like to test a particular linear contrast. The linear contrast I would like to test is whether there's a difference between the quote-unquote normal diet and the average of the vitamin and the health food diets. Okay? So now, if I write this out, I'm going to write it out every single step, just, so you get used to the idea. What I'm talking about then is right? That's the contrast I'm talking about. The mean of group 1 minus the mean of those other two groups. You don't always have to write this step out. I find it easier to think about. But you could go straight to the coefficients if it makes sense to you. Okay? Now I'm going to expand this out to get so that I have a coefficient in front of each mean. Right? So what's going to be in front of x bar 2? Actually, minus 1/2, right? And in front of x bar 3, also minus 1/2. Okay? Is this a linear contrast? How do we know? Yeah. That lets us know it's linear, but a contrast in particular, yeah? Yeah, that's right. Okay? So we have both things. It's linear, and it's a contrast, so the coefficients add up to 0. Okay? Yeah, just be careful. I mean, the truth is, any of these computations, all of you guys can do it. The only thing that people get mixed up on is sometimes they don't put in the negative signs or whatever. Make sure when you figure out your coefficients that they add up to 0. If they do, then you've done it right. Okay, I want to get rid of the fractions. What do I do here? Multiply by 2. Good. Notice something, right? I'm going to do that. Just so that it's really clear, right? So my coefficients are 2, minus 1, and minus 1. But now I want to calculate what L is. So I have to input, right? I have to plug in the means. So that's my L. It's 4.2. That's what I'm going to be testing for significance, essentially. That difference. All right, so now we're going to turn it into an SS contrast. Do I have equal ends here in this example? Do you remember? Yeah, I had equal ends. Anybody remember what was the N in each group? 5, yeah. Good. So we're going to do SS contrast for equal ends. So what's N here? 5, right? Because it doesn't have a subscript. And again, you don't necessarily have to put these in parentheses. I mean, I just do it so that it's really, really clear what we're doing. And so you don't make mistakes, but so that's my SS contrast. What's my MS contrast? Same thing, same thing. So my F is simply going to be this. I'm taking the MS within from what? The original ANOVA. Now, I have in my notes, I rounded it, so there might be a tiny bit of rounding error if you were going to do it again, but not a lot. Okay? So that's the F for this contrast. For this contrast, that's the ANOVA that we calculate for this contrast, the F. Questions on where any of those steps, any of those numbers came from? All right? Okay, so now the question, so that's calculating the F. How do we test an F usually? Yeah. I have to get an F critical value. Here's where it gets more interesting. There's going to be a difference between the F critical value that we use if we've decided on this before we look at our data or after we've looked at the data. Okay? Here, so we're going to talk about this for a couple minutes. The advantage, so if I've thought about it before, that's called a planned complex comparison. It's planned. Before I looked at the data, I planned on it. Okay? Now here's the deal. What you're looking at in your means is a pattern, or what you're looking for is a pattern. The more closely your contrast matches the actual pattern of the sample means, right? When you decide on a contrast, you're saying, I think this is the pattern of means, this is how it's going to fall out. The closer your guess is in the contrast, I don't know if guess is the right word, educated thought on, right? Compared to the actual data, then your SS contrast is going to be closer to SS between. It's going to, he says, capture more of it. It's going to have more of that. And remember, that's what you want. You want your sum of squares to be of between to be big compared to SS within. Because SS between or SS contrast, that's going to be your numerator. And that contains the pattern of the means. Okay, so you want that to be big. When the sample means do not fall out in the pattern you expect, your F contrast might be smaller than your ANOVA. It's not helpful. It's not fair to gain power through choosing a planned contrast if there's no possibility of losing power by making the wrong choice. Okay? You have to weigh those options. Again, it's when do I have more power and when do I not? You have more power if you've planned it. You have more power if you've planned it. But that only comes with the risk of planning it wrong, of getting it wrong. Okay? That's what happens. Planned contrasts are analogous to one-tailed tests. Remember we talked about one-tailed tests in a two-group design? Right? And I said a one-tailed test is only valid if before you look at the data, you decide on it. If you've already looked at the data, it's not good. It's not good. Okay? So this is analogous to that. So post-hoc complex comparisons like we do after the fact, post-hoc, are only allowed if your original F was significant, and then you have to change what the critical value is going to be. Okay? So this is the basic idea. So first we're going to figure out what is the F critical value, pretending that we planned it. Okay? So let's pretend that this was planned, if it's planned. If this is a planned contrast that I thought to do beforehand. So then the question is, what's my F critical value? What are the degrees of freedom? Well, again, always go back to what's in your F. Okay? What was the numerator of the F that we did here? MS contrast. How many degrees of freedom went into MS contrast? 1. What's the denominator? What was the denominator in this F? MS within. How many degrees of freedom go into MS within? Well, does anybody remember what the formula was? NT minus K, right. Good. So if that were the case, so it's 1 and, what were the degrees of freedom for this? I'm hearing lots of different numbers. Yeah. What was N total? 15. How many groups do we have? 3. 12. 12 degrees of freedom. So if that were the case, my F critical value would be 4.75. So is that contrast significant based on that or no? Yes. Yes. Meaning what, by the way? What's the meaning here? Yeah, it's significantly different. What was significantly different? Yeah.
The normal diet was significantly different from the average of vitamin health.
Yeah. Yeah, exactly. Yeah. The normal diet was different from the average of the vitamin and the health food together in the time it took to ride 6 miles. Okay? That was the original data. All right. Now, what do we do if it's post hoc? Right? What do we do if it wasn't planned? We have to do something called Chaffee's test. The Chaffee's test is really, really simple, actually. By the way, I think there should be an accent here. I haven't figured it out in Word yet. Chaffee's test. Now, Chaffee's test is really simple because all it does is it takes your critical value and makes it bigger. That's all it does. That's all it does. Okay? So first of all, the first thing you do, if this is a post hoc complex comparison, is our ANOVA significant? Was our original ANOVA significant? Yeah, it was. It was. So we can do this. All right, so how do we figure it out? Look at what's going on here. This is all we do. F sub S, that's Chaffee F, is equal to K minus 1 times this critical value. That's all that is. It's just finding a critical value. So for example, in this study, how many groups were there? 3. So you're doing 3 minus 1 times a critical value with 3 minus 1 and 15 minus 3 degrees of freedom. This should look familiar. Yeah. Sure. That would be useful, wouldn't it? No. Oh, this is really not taking a lot. That's the problem. Good. Better. Okay. Does this look familiar? It should. What is this? 2 and 12. That's right. It's the critical value for the original ANOVA. The critical value for the original ANOVA. So all it is 2 times. Our original ANOVA with 2 and 12 degrees of freedom was, I believe, 3.89. That's why I left it there before. So that's my Chaffee F for this contrast. All right, significant or not? But notice how much bigger that critical value is than the 4.75, right? But all we've done is we've made that critical value bigger so that we're less likely to make a type 1 error. That's all it's doing. And it's a very simple way of doing it. Okay? Had the contrast been planned, this is what I just did before. So what are the advantages to using the Chaffee F? Well, it's robust. It's robust. That's one advantage. Robust meaning not influenced by violations of the assumptions. You don't need any special tables, right? We don't need Q. We don't need any of those other Dunn's table. We don't need any of that. We're just using a simple F table. You don't need equal ends. And if you wanted to, you could create confidence intervals. We're not going to. Yes, you can be happy about that. But you could if you wanted to. Now, so what are the disadvantages of the Chaffee F? It's very, very conservative, right? By making that F critical value so big, it makes it harder to reject. It's very conservative, very conservative. Don't use it unless you're doing a complex comparison. All right? Don't use it unless you're doing a more complex comparison. Don't use it if you've decided on the comparison beforehand. Only do it after the fact. And only do it for complex comparisons. Okay? Questions on any of that? I have another big example to do the whole way through. Does anybody have questions on that? Okay. All right, let's do a big example. I have to give you the data. Okay. So these data, these are for 4 schools, okay? They have names, but we're going to call them A, B, C, and D, just because I don't want to write the names down. And these values on top are ratings of some kind, some average rating for the school. Higher numbers are better. You can't see it. Let's put the data there for the moment. And I'll move it again. This is so not fun. I have to always wear the right shirts, otherwise this doesn't sit properly. Okay, everybody got it? All right, so here's the question. First, the question is there a significant difference among these schools with respect to these ratings? Okay, how do I figure that out? What's my first test? An ANOVA. Let's just do a simple ANOVA. Okay? The ANOVA I'm going to do, by the way, Which formulas could you use if you remember the formulas at all? Right? I gave you sum of squares formulas, MS formulas for equal and unequal ends. You could use any of them because I give you all the information. All right? I did this with the sum of squares formula, so we'll do it that way. It's in your interests to go home and redo the calculations using the mean square formula just for practice. You might get slight differences because of rounding errors, but you know, it's still worth the practice. Okay, so first of all, SS between. And I'll move this when it gets all fuzzy. Okay. By the way, what's T sub T here? How do I get it? Yeah, I'm adding up all the T's. And what's NT here? Yeah. Oh, that's okay. All right? Anybody not know or not? Yeah. I just decided to do it. I'm kind of more trained to do it from the sum of squares to the mean squares, but there's really, it's just kind of habit more than anything else. If I was actually doing this for speed, I might use the mean square formulas first. Like if I didn't have to fill out a whole ANOVA table, I would definitely do the mean squares first, because then you just do the two mean squares, get your F, and go, right? Whereas if you're doing from the sum of squares, you would fill in the whole table. But it's a personal choice. Okay, SS within. And often you'll pick the formula based on what information you have. Okay. So now, having those two values, we can fill in a whole ANOVA summary table. Okay? How do I get sum of squares total? Yeah, I could add them. I could have done the other formula to check. And let's get our degrees of freedom. Let's get degrees of freedom total first. What are degrees of freedom total? Yeah, so what is it here? 23, yeah. Right? It's 1 degree off of the total number of observations. And I did that one first because, it helps you check to make sure the others are right. All right, degrees of freedom between. It's going to be here. Degrees of freedom between. Yeah, right? It's k minus 1, so it's 3 here. And then degrees of freedom within 20. Yeah, so you could have gotten that by subtraction. Or also, again, remember nt minus k, you take off a degree of freedom for each group. How do I get my mean squares? Divide across, divide across. And then the f, mean square between, divided by the mean square within. How do I know if it's significant? I have to get an f critical value. With how many degrees of freedom? 3 and 20. So, what are our results? What are our results? Significant, right? I reject the null hypothesis. There is a difference here. There's a difference in the ratings depending on the school. What's the issue? I don't know where it is. Okay? Yeah? Hang on. Let's just see if we can. I don't know if we'll get this back. Oh, good. Yes. Where? What are degrees of freedom within? NT minus K. So NT is 24. Minus K, we had 4 groups. Okay? Okay? So now we could test, and we actually are, we could test for pairwise comparisons. It's after the fact, it's post hoc. What test would I use for post hoc comparisons here, based on the ones you know? The HSD, right? Because I have more than 3 groups. We're going to do that, but we're going to do that second. The first thing we're going to do is we're going to test a contrast. Okay? Now the contrast we're going to test is this. I found out that schools A and B, actually I knew this beforehand, come from the East Coast, and schools C and D come from the West Coast. Start a little New York-California rivalry here. All right? So the contrast I would like to test is there a difference in the average between the schools from the East Coast and the schools from the West Coast? Okay, that's the contrast I want to test. So if we're going to do that, let's write that up. So this is what it is. Right? That's what it is. Like I said, for me, I just find it easier to write it this way before I get into the coefficients for each one. That's what I'm comparing, the averages of the East Coast to the average of the West Coast. So now I expand this out, and this is a very simple one to expand out. What's going to be the coefficient in front of these means? Yeah, 2 of them are going to be 1/2, and 2 of them are going to be minus 1/2. And like I said, you see it's important not to drop those negative signs by accident, because then your L will be off, and then your contrast will be out. Everything is off then. If I want to get rid of the fraction then, multiply by 2. So what's it going to be? I'm just going to put the numbers in front here just so you can see. Right, that's going to be 1. It's going to be 1s, but it's going to be minus 1 over here. So these are my coefficients, 1, 1, -1, -1. And they have to be in that order if you're putting them in the computer. I mean, when you're doing the computations, obviously, when you do them in the computer also, make sure you know the order of your groups, because it'll weight them accordingly. Okay, so now all I do is I have to put in my means. All right. That's L, that's the contrast, or the combination. Now what? What am I going to do with it? Yeah, I have to get S as contrast. Are my n's equal here? Yeah. What's little n here? What's little n here? 6, yeah. Okay. What's my MS contrast going to be? Same thing. So now I get my F. What's my MS within? Where do I get it from? The ANOVA we just did, right? So it was 0.65. Okay. All right. Now, how do we test it? We need an F critical value. Let's do it both ways. Let's say I planned this beforehand. So I planned it. So if that's the case, my F critical value is going to have what degrees of freedom? That's going to be the first one. 20, yeah. 1 and 20. Do you all know where that came from? For those of you who care, do you know where it came from? Okay, good. Okay. Significant, that contrast, or no? Yeah, yeah. Okay. If it's not planned, what do you have to do? It's not planned. If I just looked at the means afterwards and said, hey, it would be interesting to compare the East Coast and the West Coast, what do I have to do? The Shafayef. So it's k minus 1 here. 3, good. Times an F critical value with 3 and 20 degrees of freedom. That should look familiar. We did it, right? What was it? Yeah, 3.10. Now, yeah. Again, that's NT minus K. So what's NT? The total number of observations, right? 24 minus 4. Okay? All right? Now what's my decision? I would fail to reject, right? Because I'm comparing this to this. It's just, right? Just doesn't quite make it. Yeah. Say again? For phase, it's 0.05. Yeah. You're keeping it at 0.05 because you're using that F based on an alpha of 0.05, and it's just increasing it to make sure that you don't get past that.
So, but I mean, since it's so super conservative,
Yeah.
does that end up making it a lot less?
It might be. Yeah. That's a problem. Like with Tukey's also, it can be seriously less than alpha, actually. So that's always the trade-off. If you can justify it when you're doing your research, then it's okay. It's just sometimes you might submit something, and if you were a little looser in your criterion, they'll question you and say, why did you do that? Why is that justified? You know? Sometimes it is. Sometimes it's not. Yeah, but think about it, okay? I have 4 means. If I didn't look at those means and I planned something, that's one thing. But if I look at those means and say, the average of those 2 looks different from the average of those 2, then I'm stacking the deck in favor of significance. So that's why you have to be stricter, you know? Because it changes it when you look at it. Yeah, did you have a question? Planned means you decide on the question before you look at the data. I've decided I want to do comparisons on these ratings for these schools, and I've decided that I'm interested in the East Coast, West Coast difference. Now, the truth is, right, actually think about it for a minute. If you were going to do a comparison of schools in this country, would you likely do an East Coast, West Coast comparison? You don't have 4 schools. You have however many schools you have. Can you think of a comparison that you might be more likely interested in? Yeah. Public and private? Yeah, anything else that might be obvious? Yeah. Urban, suburban? Yeah. High income, low income, which might get back to the private and public options, right? There's a whole variety of different things that you might think of a priori, planned, to test. This is just, my making it up to make it easier, but okay? All right, other questions on this? Did you have a question, Eric?
Yeah, I was just double checking the plan.
Yeah.
Degrees of freedom, it's 1 because it's the MS contrast?
Yeah.
Okay.
Right, that's the numerator of it.
The MS within.
And this one?
And then the 20's from the MS within.
The 20's from the MS within, yeah. Okay? All right, one last test then. All right, we talked about it before. Let's do an HSD on all the pairwise comparisons. The only thing we don't know is the Q critical value. How do I get a Q critical value? A table. What do I need, though?
Number of groups.
Yeah. Degrees of freedom within. Yeah. I need the number of groups and degrees of freedom within. So in this example, what is that going to be? What are the number of groups? 4 and? You have it, folks. Look at it. 20. Good. So just to look, if you forget when you're trying to look up these critical values, notice something. Number of groups. It tells you. Degrees of freedom for the error term tells you. So 4 and 20 gives us a critical value of 3.96. 3.96. And then our MS within we get from before, the N we knew from before. Whoops. Sorry. Let's do it properly. Okay, yeah.
For degrees of freedom, whenever we look at those tables, you want us to go more conservative, right?
Yeah, go more conservative. Okay? What do I do with it? It's 1.30, right? And that's points different between schools. So now what? How do I use this? Yeah. Pairwise comparison, yeah.
Find the differences between schools.
Yeah, I have to find the differences between each pair of means. There's 4 groups here. You know how many differences there are? 6. Okay? So I'm going to write them out, and then we'll talk about which ones are significant.
So this is different than just that we're doing finding differences between schools.
Yeah, this is finding any of the pairwise differences. Yeah, that was a complex. I'll move it if I have to in a moment. Oh, not bad. There we go. Okay. All right, so let's go back and see what's significant. What about the difference between A and B? Is that significant or not? Yes, does it matter that it's negative? No, right, because we'll look at the magnitude. What about between A and C? A and D? B and C? B and D? C and D? What's my conclusion here? There's an easy way to summarize this. And if you actually looked at the means to begin with, it would help you. Yeah. Yeah, right? B is the different thing, right? B is significantly different from the other 3, but the other 3 aren't different from each other. It's very useful, especially when you're doing lots of groups, to kind of try to make it as concise as possible. See where the patterns are. The pattern here is that B is different from everybody else. Okay? Questions on that? This is typical. This is much more typical than, I taught you how to do a 1 sample test. That like never happens. This happens. This happens. And people go back and they do all these elaborate analyses to try to figure out where the differences are. Okay? So this was with 1 a factor, independent groups, right? With multiple comparisons to follow. What's going to be the next thing we do? Two factors. Two factors. All right? This is one factor, one independent variable. The next topic, we'll start that next week, is what happens when you have two factors involved. Okay? We are done for the week. Have a good one.